Alright, so now we're going to be looking at some additional trigonometric identities. So in the Pure 1 book, right, we learned about the identity sine squared plus cos squared is 1. And from there, we can actually deduce two more identities. And I've written them out for you in this page. So the first one is 1 plus tan squared is sec squared, and 1 plus cot squared is cosec squared. And as I said, they are actually derived from the original sine squared plus cos squared is 1. So just to show how it's derived, if we start off with sine squared x plus cos squared x is equal to 1, and then I'm now going to divide every single term by cos squared x. If I was to do that, then I'll have sine squared x over cos squared x plus cos squared x over cos squared x is equal to 1 over cos squared x. Sine squared plus cos squared is tan squared. Sine squared over cos squared is tan squared. Cos squared over cos squared is 1, and 1 over cos we know is sec, so it's going to be sec squared x. And as you can see, that's how we get the first equation here. And as you would guess, the second equation, we just divide everything by sine squared. So it's just a very simple proof of just getting two more identities, which will come in handy for later on when we're solving these trig problems. Right, so as we said, with those identities, we can actually do more proofs, more solving equations, more simplifying. So let's try a couple of proofs together. So let's maybe go for C. So we have left-hand side is equal to sec squared A cot squared A minus cos squared A. Just because we've learned those two extra identities doesn't mean you automatically have to use them. The way we do proofs still works, where we just simplify into sine and cos. That still should apply to most proofs. So if I change these to now sine and cos, so we have 1 over cos squared A, and then in brackets we have cot is cos over sine, so cos squared over sine squared minus cos squared, which now I can just multiply out the bracket, right? So then it will cancel out to 1 over sine squared A minus 1. 1 over sine squared is cosec squared A minus 1. And we know from this first identity that we've looked before, cosec squared minus 1 is cot squared, right? So this I can say is equal to cot squared A, which is equal to the right-hand side, and that's what they want us to show. Right, let's try question E. So we have left-hand side is equal to 1 minus tan squared A over 1 plus tan squared A. Remember when we're doing proofs, right, the denominator, we always want to try and make it into one term, right? So we have two terms here. So luckily for us, we've learned that the new identity 1 plus tan squared is sec squared. So I can say that it's 1 minus tan squared A is equal over sec squared A. Okay, now I can just change it to the sine and cos terms. So we'll have 1 minus sine squared A over cos squared A. And on the denominator, we'll have 1 over cos squared A. I can make these fractions a bit simpler. So the numerator I can rewrite it as cos squared A minus sine squared A over cos squared A. In the denominator, I have 1 over cos squared A, meaning that these will cancel out, right? Cancel. So we'll be left with cos squared A minus sine squared A. We know that cos squared A is equal to 1 minus sine squared A. That's how we get this as 1 minus 2 sine squared A, which is equal to the right-hand side that they wanted us to show here. Okay. And lastly, maybe you can try this G1 here. So we have cosec A sec squared is equal to cosec plus tan sec. So left-hand side, cosec A sec squared, starting off with this. Right, first things first, we just want to change it up a bit. So maybe sec squared we know is equal to 1 plus tan squared, right? So I can change that. So I can say cosec A 1 plus tan squared using the identity we just learned. And then I can multiply out the brackets, or I can even like simplify to sine and cos, right? So I can say 1 over sine A, and in brackets I have 1 plus sine squared A over cos squared A. If I multiply out the bracket now, I'll have 1 over sine A plus sine squared A over sine A cos A, meaning that one of the signs will cancel out, right? So we'll be left with 1 over sine A plus sine A over cos A, which we can rewrite as cosec A plus tan A, and that's what they wanted on the right-hand side. So as you can see, just because we learned there's two new identities, we can incorporate them in some stages, but the main premise that we just changed the sign of the cos is still applicable to these kinds of proofs. Okay, so like in the pure book 1, we can also find exact values of sine terms using these identities. So the finding exact values is still the same. We still do the triangle, or you can do inequality method, or the identity method, sorry, and making sure you choose the right positive or negative values. Once again, if you may be unsure of this method, maybe go back to the video where we look at finding exact values for trig. Right, so starting from here, we have 3 tan squared theta plus 4 sec squared theta is equal to 5. And they told us theta is obtuse. Obtuse, we know that means it's between 90 and 180. This will be useful later on when we find whether it is positive or negative. So first things first, we want to try and change it into one term. So we ideally want to change the tan, because tan is just easier for us to use. So we'll have 3 tan squared theta plus 4 sec squared, once again, is 1 plus tan squared is equal to 5. And just expand the bracket. So we'll have 7 tan squared theta plus 4 is equal to 5. So tan squared theta is equal to 1 over 7. So tan theta is equal to the root of 1 over 7. And this is plus or minus because we're square rooting, right? Now this is where we go about finding whether it's a plus or minus term. So we draw this cast diagram, CAST. We know that it's an obtuse angle, so it has to be in the S section, which means that only the sine term is positive. So this tan theta, in fact, is going to be equal to negative root 1 over 7. Right, from here, we need to find the sine value, right? So I'm going to use the right angle triangle method. You can use the identity method, but I found this is a bit easier. So theta, so tan is opposite of adjacent, so this is root 1, root 7. So therefore, this is root 8. So we can have sine theta is equal to root 1 over root 8, which is the root of 1 over 8, and it's a positive value because we know S is in the S section here. So the method for finding is just the same. It's just initially using an equation, just using the identity we've learned, just to simplify it a bit. Okay, so using these identities, we can also solve for theta values in certain intervals. So the method is still the same, it's just that we might need to incorporate or use these identities to manipulate it a bit. So maybe let's just try E. So we have 3 sec a half theta is equal to 2 tan squared a half theta. And that is between 0 theta and 360. Right, first things first is something other than theta, right? So I'm going to replace that with a capital A. So let capital A is equal to half theta, meaning that we should also change the interval for A. So A is half theta, so we just divide theta by 2 each time. The interval for A is going to be between 0 and 180. Next, I'm going to replace the tan squared, right? Because we can replace it in terms of sec. Well, we want it in terms of sec, because we ideally want the same trig function. So we're going to have 3 sec A is equal to 2. And I can use the identity that 1 plus tan squared is sec squared. So this is going to be sec squared A minus 1. Expanding the bracket and bringing it all to one side will leave us with 2 sec squared A minus 3 sec A minus 2, which I can now factorize, right? So 0 is equal to 2 sec A, and what we're going to have minus 2 plus 1. So therefore sec A is equal to negative a half, and sec A or is equal to 2. Right, from here, it's just finding the A angle. But remember, we don't have sec on the calculator, so we have to change it to cos, just like flipping it, right? So cos A is equal to negative 2, or cos A is equal to 1 over 2. As you can see, we have here cos A is negative 2, but we know that cos can only be between minus 1 and 1. So this is actually not going to give us any solution. So we're just going to be left with cos A is a half, which we can find A. So A is going to be inverse cos a half, which will give us, in terms of degrees, it'll be 60 degrees. Drawing my cast diagram, CAST is going to lie in the A section and in the C section, 60, 60. And as you can see, A is going to be 60 degrees, but it's only between 0 and 180, right? So that's the only example, or only answer. And theta being 2A will be 120 degrees. Okay, so the latter part is just the same. It's just that initially we had to use the equation to form it into a better, or just manipulate it a bit. All right, maybe we can just try one more. So if we try this, cot theta is 1 minus cosec squared theta. So cot theta is equal to 1 minus cosec squared theta. And that's between 0 and 2 pi, so it's going to be in radians. So same thing, we want to replace it, make it the same term. So we know that 1 plus cot squared is equal to cosec squared, so that's what I'm going to replace my cosec squared with. So therefore we're going to have cot theta is equal to 1 minus 1 plus cot squared theta, which means that we're going to have cot theta is equal to cot squared theta, 0 equals equal to cot squared theta minus cot theta. So therefore, remember, we don't want to cancel that. We never want to cancel because we might lose solutions. So rather than that, we're going to factorize. We're going to have cot theta minus 1. So therefore, cot theta is going to be 0, or cot theta is going to be 1. We can change the tan, right, by flipping it. So tan theta is equal to 0, or tan theta is equal to 1. Remembering it's in between 0 and 2 pi. So in radians, theta is going to be 0, or it's going to be pi over 4. Just simply plugging it, or using the class diagram, it's going to be here or here for 0, and it's going to be between in the A section and in the T section for the other one. So the final solution, theta will be 0, it will be pi over 4, it will be pi, and it will be pi plus pi over 4, so 5 pi over 4. Those are the 4 solutions that we'll get for this answer. All right, and then finally, I just want to go through some more rearranging equations using these identities. So this here, so which we have 2 sec squared theta minus tan squared theta is equal to pi, or p in this case, and they want us to find the solutions for the exact value of cosec squared theta. So we will try and manipulate this to get cosec squared. The first things first, I have 2 lots of these sec squareds, right? So I can replace it by saying sec squared plus sec squared minus tan squared is equal to p. And the identity we've learned is 1 plus tan squared is equal to sec squared. So if I move this tan squared to this side, or sec squared minus tan squared is 1, meaning that this is equal to 1. So I can say that sec squared theta plus 1 is equal to p, meaning that sec squared theta is equal to p minus 1 like this, right? What can we do next? Well, sec squared is 1 over cos, so cos squared theta is equal to 1 over p minus 1. And we know, well, cosec is 1 over sine, right? So ideally, if we have sine, then we can just flip it. So how do we relate cos squared and sine squared? Well, that's just the first identity we've learned in the year 1 book. So sine squared theta is equal plus cos squared is equal to 1, meaning that cos squared theta is equal to 1 minus sine squared theta. So I can say that this I can say is equal to 1 minus sine squared theta is 1 over p minus 1. So rearranging for sine squared, we'll get 1 minus 1 over p minus 1, which I can just simplify a bit further, giving us p minus 2 over p minus 1. And note, this is sine squared, right? But we want cosec squared, so cosec is just flipping up and down. So we'll end up with p minus 1 over p minus 2, so which they wanted here. So as you can see, we're just using these identities, and we're using just a combination of all these different identities. And that's why you need to be very careful, or be very familiar with how they are linked together, what's linked with what, and how we can arrange them together.